All right, welcome back. Welcome to the last lecture for CS234. What we'll do today is we'll do a review and a wrap up, and we're also going to discuss the quiz a little bit. But before we get started, I just wanted to remind us where we are. So last time we did the quiz. Today we have sort of a review of the course and looking forward. So what we're going to do today is we're going to sort of do a combination of the quiz recap and then looking forward to sort of reviewing some of the things we've done in the class as well as looking forward. So we're going to jump into the quiz. The quiz will have back to you guys within about a day. And we're just going to step through some of it because I think it's a nice summary of sort of some of the different aspects. So we go to the quiz. I'm going to start on question 3. So the quiz, as everybody knows, sort of was comprehensive. It covered the entire course. We're not finished grading it yet, but we noticed that there were some problems that people had more challenges with than others. One quick clarification is that when we said a justification for your choice, we expected you to put something different than the choice itself. So we wanted you to actually provide an explanation or rationale for why you picked what you did. So let's just step through the quiz, and inside of the solutions we'll also do that. You might have noticed that the second question was identical to the midterm, so it was a good chance to refresh if you hadn't remembered that from the midterm. The third one was slightly tricky, so I want to just make sure to go through it. It's a nice way to review PPO. So the third question really asked you to think about proximal policy optimization, which was something that you implemented. And one thing that might have been slightly confusing or a good thing to refresh is that we really emphasized in class that PPO allowed us to use data and make multiple gradient steps. And when it made multiple gradient steps, those would be off policy. But the very first step that PPO makes is always on policy. So this is true because if you've just gotten the data and then you're doing a policy gradient step on that, that part is considered off on policy. After that, you're trying to take a further step. So if we had sort of a one-dimensional policy, your first step is going to be on policy, and then any further steps you take are now going to be off policy using data that you collected from the previous round. So I know that that was often a good thing to make sure to refresh. And the second part was that we do not have any guarantees on B. And the third part is true. And we want to emphasize here that we're only doing importance sampling over the actions. What PPO does and what some of the other algorithms it was inspired by do is that they don't try to directly handle the state distribution mismatch. And instead, they try to create a new policy that's close enough that they hope that the fact that you're going to be visiting different states under a new policy is only going to be slightly observed. And the last is that you can use lots of different types of advantage estimators. And so the D is not true. You could use generalized advantage estimation, but you could also use other methods as well. And throughout this, if anybody has any questions, feel free to ask me. So the fourth question was given by our guest lecturer. For those of you that had a chance to attend or to watch it later, he talked a lot, Dan talked a lot about thinking about the alignment problem and thinking about what things are important for that. The first part is not true. It's generally hard to think about, there's different ways to think about autonomy, but that was not what we were focused on. The second one is true. So one of the things Dan talked about a lot in his lecture was the fact that often when we think about preferences and alignment, we often are focusing on people's individual preferences. Like someone says they like option 1 instead of option 2. But that focuses really on the utility to a single individual as opposed to the implications for the broader society. And so the second one is true because, as Dan brought up, moral theories give us a way to think about more broad benefits to society and to collections of individuals instead of to individuals. He also talked a lot about how autonomy is often a core principle when we think about the value of different decisions we can make. And so the idea of an AI agent to allowing people to have some autonomy would say that an AI agent that thinks about someone's suboptimal decision, so it might be that somebody really wants to do something that we know is not very good for them, that an AI agent that is aligned and allows that person autonomy would still maybe support that because in the interest of sort of upweighing the degree of autonomy. And the last one is also true because you could think of this as a form of paternalism. So if the agent decides, well, it's not really a good idea for you to smoke, and so I'm not going to tell you where you can buy cigarettes, that may or may not be true. Of course, we know that smoking is causally associated with lung cancer. So you could imagine that case, it's not in their best interest, but that would be considered a form of paternalism, and so that would undermine user autonomy.
Yeah, I don't know if I agree with C even with the explanation, because it seems to me that best interest and suboptimal decisions are like definitionally, well, best interest entail like optimal decisions, and you're saying we should let the user make a suboptimal decisions. I don't see how those are. If it is in fact in the best interest of the user to make decisions, then those decisions are no longer suboptimal, which would be a contradiction, it seems to me. I don't see how that follows.
It's an interesting question, right? So I think what it says here is that there is different notions of what the objective is, and there are different notions of what is considered optimal or not optimal. So there might be some cases where for general population or even for humans in general, there is one part of your reward function that says this particular decision, like smoking cigarettes, is not considered to be optimal because of long-term health outcomes. However, you might have another part of your reward function that talks about the importance of user autonomy. And so if you value user autonomy higher than, say, someone's health, perhaps in this particular instance, for that particular constraint, then in that case you might say, well, if I'm supporting that person, so if the user's best interest, if the best interest of the user is to more value their ability to have autonomy than for them to make this particular health decision, then you would give them the information about where cigarettes are. Yeah.
Yeah, I was also like just the first clause, since it is in the user's best interest, I thought like it's really hard to generalize about what a single user's best interest was, and so that was not a true statement in like by the start, because maybe some people aren't best making their own decisions about things, and so I wasn't sure how confidently you could say that.
Yeah, it's an interesting question. So what Dan argued is that it is generally a principle that everyone needs some amount of autonomy. And so if you go with that argument, then you would say, if we believe that it is important for all of us to have some autonomy, then under that should also allow us the freedom to make bad decisions some of the time. And in that case, an LLM that is supporting us also needs to be able to respect those bad decisions. And you could disagree with this. You could disagree with like that as a premise in terms of the type of theories that promote that everyone should have autonomy. And we give different people in society different amounts of autonomy. Children generally have less than, adults. But if you assume that that's the case, as long as you assume that like it's always important for every individual to have some amount of autonomy, that would include allowing them to make bad decisions sometimes.
If our justification says like that's not something you can assume, how would that be?
I don't know how that exactly was great. I didn't grade this particular question, but you can definitely see what they say in terms of that. And yeah, we will look at everyone's justification in terms of that. Good questions. The next one that I wanted to go through was Monte Carlo tree search. So this is another one that people, there was a little bit of differences over in terms of whether this was something people had some questions on. So the first one is true. So Monte Carlo tree search, the MCTS, the M in the Monte Carlo tree search stands for Monte, not for Markov. So and the way that we described it in class, you can use it in both. So what we do in Monte Carlo tree search is we sample from the dynamics model to get to a next state. And as long as we can sample from that, whether that's a Markov model or if you required all of the history so far in the tree to make that dynamics, that would be okay. So there's not something inherent in Monte Carlo tree search that means you always have to have a Markov system. The second is true. So the way that Monte Carlo tree search uses sampling is it samples the next state. And what it does there is it means that instead of having to enumerate all possible states, you can just sample a subset of them and still get an accurate estimation of the expectation. And the fourth is false. So this is not true because in this case, like in a lot of settings, including AlphaGo, the reward model is known. So we're not trying to learn the reward model. But upper confidence bounds are still useful because they allow us to prioritize among the actions, because ultimately we want to be thinking about taking maxes. And so in these cases, upper confidence bounds, like upper confidence bound trees, are using UCB to sort of actively think of how we're expanding out the tree. And then the fourth one is also true, because that's exactly what AlphaZero does, is they use self-play to improve the network to predict values and action probabilities. Yeah?
The third one is true or false?
False.
It's false.
It's false. Yeah.
I'm a bit confused about the fourth wording. It says Monte Carlo tree search is used in AlphaZero, but doesn't AlphaZero use a different variant of a tree search that is not Monte Carlo? I am a bit confused.
AlphaZero uses Monte Carlo tree search. It uses Monte Carlo tree search with self-play to train a network that predicts values and action probabilities. That's part of what it does.
Well, wasn't there a different thing that had the word confidence in it for it?
Oh, upper confidence trees?
Yeah.
Yeah, so it uses a particular form of upper confidence trees as well. So upper confidence trees is a type of Monte Carlo tree search. It's like Monte Carlo tree search is a superset of UCT. Okay. So, and let's go through these two, because all of these are true. And so I think this is a useful one to go through as well. All right, so ChatGPT did learn rewards from humans preparing preferences over prompt output pairs and then used PPO to train a better prompt. So in fact, they did a ranking, but they did do this. In general, for long horizon problems and really large action spaces, that would be somewhere where a forward search would be really expensive to do. So using something like AlphaZero, which essentially builds a subset of the tree search, can be really helpful. In PAC, probably approximately correct methods, we are guaranteed to learn an epsilon optimal policy, but the epsilon might be non-zero, which means we're not guaranteed to learn an optimal policy. So if you want to get if you're okay with your kitchen being like slightly messy, which I am, then it would be okay to use a PAC-RL algorithm that would make a finite number of mistakes, but most of the time would keep your kitchen pretty neat, but maybe not perfectly neat. And then offline RL may be particularly beneficial for healthcare and other high-stakes settings where online exploration might be risky or very expensive. So in this case, all of these were true. All right, and then the next one I was going to talk about is 9, where we go through some of the theoretical properties. So in this case, what we have is that optimism, in this case, the first one is not true because we don't have any guarantees in general for the reinforced algorithm. The second one is true for the reasons we just said. A PAC algorithm guarantees your epsilon optimal. So this is, but not necessarily fully optimal. In the third case, it is not guaranteed to have sublinear regret. So this is false. And the reason, again, for this is that if you just get an epsilon optimal policy, you might make epsilon mistakes for the rest of time. So like epsilon times t, which would still give you a linear regret. The fourth is also false. So in general, you can think of just minimizing regret, which is the difference between your policy and the optimal policy, or maximizing expected cumulative rewards. And they're just the same thing. One you just subtract from the other. You can either maximize cumulative regret or maximize cumulative reward or minimize regret. And then in the fourth case, this will not necessarily be a PAC algorithm. So the only one in this case is only B is true. And the reason for this is a PAC algorithm has to make a finite number of mistakes. So it normally has to be polynomial. And so even this would say this algorithm would be consistently converging to the optimal policy, but you don't necessarily know how long it would take. So it could be very expensive. And then the final question has us think about which algorithms could generate the observed reward. Raise your hand if anybody wants me to go through that. I'm happy to and step through it, or otherwise we'll move on to the next part. Allow people to just think about how different algorithms would run and whether or not they could generate this observed data. All right, well, we'll release the solutions for the quiz over the next day, and we'll also release the solution, the grades. Yeah.
So in back, like, does the definition mean that we're only allowed to make finite number of mistakes, or is it that your total mistakes should be within some budget?
Finite number of mistakes. So great question. So in terms of PAC, what we normally require is that the number of mistakes made, well, with high probability on all but a finite number, you will be epsilon optimal. And that finite number needs to be a polynomial function of your problem parameters, including like 1 over epsilon, the size of your state space, the size of your action space, etc. So, it doesn't always tell you when those mistakes will occur. They may be at the beginning or they may be later.
I was thinking if you could have some sort of decay rate into mistakes, then it would still be fine as long as their sum is within some bound, like Robinson-Monroe sequence you have in that sense.
Yeah, I mean, you certainly could do that. It wouldn't be PAC unless you could guarantee with high probability that that total number of mistakes would be small. Yeah, it's a good question. One thing, some of the work that we have done in the past is you may or may not know what epsilon you want to commit to in advance. And so we've also developed algorithms where you could think of this occurring for different epsilons. Maybe as you have different amounts of budget, you might want to be able to pick epsilon. Because if you get a lot of data, maybe you can get more optimal. Good question. Anybody else have questions about the quiz? All right, well, feel free to, we have normal office hours this week, so feel free to come to our office hours. Next week, we will not have office hours anymore, but if you have any questions about the quiz or about your projects, feel free to come see us. All right, so I think it's always exciting to go back to the beginning of the quarter and kind of think back of all the things that we've covered, as well as looking forward in terms of the field. So when we started the very first lecture, the slide might look somewhat familiar, we talked about how reinforcement learning is fundamentally the question of learning through experience to make good decisions in order to optimize our long-term reward. And so that's really the central question that it tries to start to answer. And we talked about there being a number of different learning objectives in the course. And so what I hope that people will walk away with from in this class is to understand what are the key features of reinforcement learning and how does that change compared to supervised learning and AI planning and a lot of other areas, or unsupervised learning. To understand how, if you're given an application problem, whether and how you should use RL for it, and what algorithms might be appropriate. To be able to implement in code RL algorithms, and you guys have had lots of practice with that. And then to understand how we would compare and contrast about what it means to have a good RL algorithm and what are the sort of ways we should evaluate algorithms themselves as a way to help us understand if we're making progress. So thinking about things like regret, sample complexity, computational complexity, empirical performance. Does it converge to the optimal policy? Does it converge at all? And then also to understand the sort of exploitation challenge in terms of data collection. And these sort of fundamental challenges we have between the data that we gather, allowing us to learn things about the environment and about different decision policies, versus using that information to actually obtain high rewards. And so throughout this, you've had a chance to think about this on the quiz, on the midterm, on the homeworks, and then now also in your final project. So what I'd like to do now is to sort of, again, revisit this second question, because I think really as you go forward, this will be when you use reinforcement learning, this is going to be one of the things that you'd constantly have to do, which is to decide for any new problem you're looking at, is it appropriate to think about reinforcement learning as a tool to help you solve that problem? And so I think to do that, it's helpful to go back to the motivating domains from the first lecture. So three of the domains, we talked about a number of different domains throughout the class, but here are three of the domains that we talked about on the first lecture. So the first one is alpha tensor. This is alpha tensor. And in alpha tensor, the idea was to figure out a more effective algorithm for learning to multiply matrices. And kind of the amazingly beautiful thing they did in that case is that they actually are doing reinforcement learning to learn algorithms, which I still think is really incredible. It's extremely creative. And so What they want to think about in this case is if you want to multiply two matrices, this is just 2 by 2, but they go beyond that, what is sort of the way we should operationalize that so that we can think about the particular products and sums that we're doing in order to reduce the amount of computational complexity we need to accomplish this in a correct way. And what the researchers at DeepMind were doing when they were thinking about this is they were thinking about a common task that comes up everywhere. We multiply matrices all the time for almost all of AI and machine learning. And so we're really relying underneath, there's constantly that cost that we're doing. And so they're thinking about, can we essentially invent better algorithms for doing some of these really basic substructures? So I think that was really exciting. And I think this is one of the domains that that now you have some of the tools to be able to do the same types of algorithms as what they use to solve this. Bless you. So what I'm going to do right now is I'm going to revisit these three, and then I'm going to ask you to think about how, given what you know now, how you would formulate them. And some of them I've talked about a little bit more or a little bit less, but I'll first just give you a quick refresher so you can think about, given what you know, you might formulate this. So the second one was plasma control. And this is much more of a controls-like, more like the Mujoko type of task that we saw, where they're trying to manipulate and control these different plasma, and they want to think about a control policy to allow you to achieve different types of configurations. And then the third one was thinking about how do we figure out who to test given finite resources. So this is for COVID testing. So if you have a bunch of people coming off an airplane and you have a finite number of tests, who can you test to better understand who might be sick and restrict the spread of COVID? And this is a process that's happening, every day as people are flying into Greece, into different airports, and then you would send off those samples to labs, and then a few days later you would get the results, and those people that you asked to test could come out of quarantine. And so what I'd like you to do now, and I've posted a poll for this, is to think about the following. So I'll label those as well. This is the alpha tensor. This is plasma. And this is COVID testing. If you can go onto the poll and say, which domain are you choosing? Is it a bandit? Is it a multi-step RL problem? What type of problem is this? What setting are we in? Is the problem an offline setting or an online setting, or some combination? What do you think the state, action, and rewards might be? And what algorithms do you think you would use to try to tackle this problem? And we'll take a few minutes to go through that. All right, we'll give a few more minutes and then share some of our thoughts. And I think one good thing to think about in this too is like, are there problems with distribution shift that might come up? Are there cases where we'd want to be conservative with respect to the results that are being generalized? Or do we not have to worry too much about distribution shift in these cases? Like, could there be unsafe states or too risky or things like that? So I think we actually have a nice breakdown. Raise your hand if you did plasma. Is there someone else here? Oh, so we do have another person doing plasma, but they are remote then. Raise your hand if you did COVID. Okay, maybe you want to go near those guys so you guys can all compare your answers. And then, did you guys both do alpha tensor? Okay, perfect. Well, so why don't we take a minute and talk to your neighbor, and I'll also come around and see if you guys came up with the same formulation.
Plasma. I said plasma is shrinking in 3D space, so I have a tensor with values of the plasma density as my state. Yeah. It would be a multi-step analysis, so if you like take an action to control it, you will get a different state.
Yeah, there are two ways to approach it. One is
So that's that. I said it would be good to do this offline because I was like, if I go to it, it's dangerous to have plasma.
Yeah, that's what you're saying. I'm not a biologist. Yes.
Yeah, so
But then also, it's one to run it online. So what do you do in like these? Like, would you do like model-based RL on kind of like a simulator, or like Q-learning, or like?
So yes, it's Q-learning. Well, I didn't write this down. I think it would be good to have a fast system because it's a real-time system and it's not.
Right, you can't be like plasma stop.
Yeah, exactly. So research or anything of that sort is out of the thing, let's say. Yeah, so I think it would be a Q-learning system of some sort. I suggest ECQ. Because, yeah, also like hopefully have a lot of data to be trained on before we try to train another algorithm. So that's what
how would they
or maybe simulation. I don't know how plasma simulations work. So
the actions?
Yeah, and that's just I was just talking the other day. Someone said that a lot of what they're interested in is kind of engineering is taking their really expensive physics simulators and then making it cheaper. And then putting it on top of that. So in this particular research paper, they did legal simulator, and so they do actual research on top of that simulator. But you're right that like they have to be carefully about how to choose that. So I'll go over in a second and we'll do some customization essentially.
Yeah, there's those features that represent.
But yeah, I agree with you. Like, go to the final way it hopefully works.
Yeah, that was targeted.
Cool.
And then action is just
Yeah.
What
you guys think
about
it? What was the rewards for you guys are doing coding?
I'm not sure like how to like okay, what I put down was like total number of test cases of like the country, but like that doesn't represent like the people being tested. It's like using some sort of proxy. So I mean you could also do like total number of negative cases. But there has to be some way to include that population. But like
that would be the hope, at least, yeah. Unless you really proxy it and you could say like it's the maybe it's like the discrete number of tests, it's fixed number of tests, and then it's the number of possible cases and catch. Measure that square. Otherwise, it's very downstream. You know what I mean? To like see like they tested positive. How do you know it's those ones that are and stuff? So I think here for the mandate, I think that each of them like for their work, all of it, because they
Like
would
finding state legally
Yeah.
compare to. But it has, as you said, it has. What do you think with your online, offline?
We're not sure, but like now that it looks like some combination also makes sense. Like I was thinking it was closer to offline because there's like this batch setting with delay. You have to make decisions for multiple people. A delay from when you test the results. But then it's online, so that's like, you know, you have people entering,
You know it.
like
Models.
Yeah.
Always learn.
like
That's right. I guess I'd probably call it batch online.
Yeah.
It's online, yeah, because it's all, they don't have historical data that they're really leveraging, so it's all online, but it's just the results from the data.
Yeah, I was like, I wasn't really sure about how to measure the words. Like,
Yeah, I guess. Well, then maybe like, so Sophie, what do you think in terms of algorithms? What might you use?
Because then every
Like, what are the words that and it's the better? Do you want to do exploring? But
yeah,
do you guys
Yeah.
remember what was the
Yeah. So simply like creating
Is it terms?
actually some other like unreasonably major examples.
That's right. And so if it's batch, do you guys remember the question?
Well, I think you can just have like a very like infinite reward.
That's right, exactly. Good. Yeah. So so for the Thompson sampling, we samples from the prior, and so then
You would just
yeah,
be like
so that's one of the
infinitely
places.
substandard.
I think this is a nice motivation for why you might do that outside of like customers and stuff. Like because they don't have to be
actually, that really grounds the distinction
Yes.
between the two for me.
Yeah, because they really want. I mean, you kind of get some exploration that like they have features of people. So like you get it's not like everyone would necessarily get the same, but in general, if there were two people that look like so if maybe you guys look identical in terms of the features coming in, actually always get the same decision, and so that really boosts them.
Cut off every episode.
So I feel like Thompson sampling is kind of a cool way to do it without having to think about it.
Describe the final terminal state. Then you have someone every step you get, you lose.
Yeah, I guess what I'm saying is, I think what you guys are there's just so many ways you can find what is this. But what I'm saying is that I think one way at least
to
if you so the problem in general if you say about
for
I
each
don't know
step
what's based on everyone who testified but it's tested
the
is
maximum episodic.
and so then
So if you,
so
for example, if you just went through all the steps and you learn such and you get that reward of 0, pretty yeah. If you went longer, you just join it.
But I agree that like really could be also some other considerations you'd like to like maybe figure out the people who test positive
Yeah, I
who are going to go to the cities or things like that, right? Because if someone's going to go on a farm, maybe it doesn't matter as much. But if they're going to go to like Seoul, then and I don't think any of that was taken up there at the downstream. Let's come back together. I really like these domains. I think that they're really interesting domains to think about sort of what is the implications for how we model these and the choices that we have to make and what are the algorithms that would work. So let's go through some of them because I know that a lot of people pick different ones. So alpha tensor, because I think because I know there's some people who are watching online remotely because we have more answers as well. So I think it's really interesting to see the perspective. I'm not sure that there was very few people that mentioned Monte Carlo tree search, but actually for alpha tensor, it is something, I guess maybe the alpha should hint at that, like AlphaZero, etc. So it is something where they're using reinforcement learning and policy networks, etc. But they're also combining it with kind of AlphaZero-like technology. So they use Monte Carlo tree search in this case. So they have Monte Carlo tree search. So this is a reinforcement learning problem. It's multi-step because the idea is that you want to take a series of steps until you solve the multiplication problem. And what the steps are in this case is you could think of it as like algorithmic steps. So like, which parts of like if we go back to here, let me just make this big for a second. If you think of this, when you do matrix multiplication, you have A1 times B1 and A2 plus A2 times B3, A1 times B2, A2 plus B4, etc. You can think of there's all these different products and sums, and you could do them in different orders, and you can kind of refactor that. So when you think about sort of all the operations you could do, you're going to have to do a series of operations such that, remember, what they're trying to learn here is not how to multiply two particular ones, but they're trying to learn the algorithm that will always correctly solve in the minimum number of steps. So here their reward function is the number of steps, the number of computations that you have to do. And of course, it has to be correct. And to me, one of the brilliance of their ideas is how do you make sure that you're only searching within the space of correct algorithms? And so there's some really nice properties for this particular problem that allowed them to do that. Some other people had also noticed this in the past. And then what they said is, oh, given that we have that, given that we have a way to verify that, and only search in the algorithms that are correct, now what we can do is just optimize for length. And so the way that they do that in this case is they're going to, very similar in certain ways to AlphaZero, be able to search through different, using like policy networks and value networks. So you can see here they have a neural network with both a policy head and a value head, similar to what we saw for AlphaZero. But they are going to do this forward search. Now, one of the interesting things about this is that compared to what we saw for AlphaGo, in AlphaGo, because I saw we talked about this with some of you and saw that in your notes, at runtime, they're not going to do search anymore. What they're going to do at this point is they're just trying to find the best possible algorithm. And then in the future, they're not going to do any additional Monte Carlo tree search, unlike what we do with playing Go, because the assumption is at that point they have the algorithm and they'll just apply it to multiplying. So they don't continue to do Monte Carlo tree search kind of at runtime. This is all something done just to find that best algorithm. So this is a case where we would have Monte Carlo tree search, and we would also have policy networks, policy and value network, and where they're sharing, again, this is sort of, a single neural network, so you can get shared representations here, very similar to AlphaZero. And then they can play in this case. Yeah? How do they overcome distribution shifts? Here, they are trying to have, so all of the algorithms they search through are correct. So there's no distribution shift in that, like, they will always be correct for a future problem. It's just that it may or may not be that they found the very most optimal one. So there's not kind of the same problem that you might run into different states. The nice thing here is it's just a series of operations. It may be that the search is stuff that they didn't find the optimal one. So there might be still better algorithms that are shorter. I don't think they proved this was a lower bound, to my knowledge. And so it's a great question. There's not going to be a problem with, like, when you deploy this on a new matrix multiplication that you might get something wrong. It's just that, it may or may not be the most optimal way to multiply that particular two matrices. So I think that's sort of the cleverness of having the policy network be, or having the space they search over always has fine correctness. Yeah.
Were they able to interpret the algorithm or learn something interesting or intuit what was going on?
Yeah, it's a great question. So what, was there sort of some kind of high level insight, and in particular high level insight you could translate to other problems? Not that I remember. I think that I don't remember there being any sort of particular aha moment, now this means for all these other type of problems we can do this. But it'd be interesting to go back to the paper and see if there was anything that I missed in that case. So I think what they found in this case, to what I remember, is that they've relearned a couple different well-known algorithms for trying to, during the search process. They learned a couple algorithms that are known to be good and more effective, and then found some others that hadn't been discovered before. And so I think there's also an interesting question, because there may be other sort of utility functions for downstream use of these algorithms. And so in that case, you might want these approaches to sort of provide you a set of solutions, a set of algorithms, and then people could pick, which ones they thought were best. All right, so this is a multi-step RL problem. And here, the state of the system would essentially be, what are the operations you have so far? So what are the operations that you've done on the input two matrices specified as tensors? and then how far do you need to go until you can get to the complete solution. And the reward in this case, assuming that you've conditioned everything on being correctness, is just length. All right. So next, let's go to learning plasma control for fusion science. And I think this is a really interesting one. I appreciated that I saw for a lot of people saying like, well, you don't want to do, like epsilon greedy on real R with plasma. That's probably a bad idea for all of our health. So there's need to be like some form of offline phase. And that's exactly right. Like that's certainly what they did in this case. I think it's interesting to sort of think about how it's represented and sort of the different types of controls you'd be applying in this case, which generally will be real valued. So it's a very different problem than alpha tensor. Let's look at sort of what their architecture was. So in this case, one thing that they also really emphasize in this is that they had to spend quite a long time, or they had to think really carefully about what is the objective. So this is an interesting one. It's not just like minimize, the number of computations to solve two matrices. It's saying we want to be able to kind of manipulate plasma into particular configurations. And so you could imagine in this case, you might have lots of different reward functions and you want to be able to quickly learn policies for those. So what they do to ameliorate the offline safety issue is they build a simulator. And I was just coming to someone that on a recent panel I was on, I was talking to a mechanical engineer that said that's one of the reasons they were really interested in AI and machine learning is they like to make simulators of really computationally expensive physical processes. And so they here have a simulator that is fairly high fidelity, but not perfect, and is high fidelity enough that they think it'll be useful, but low fidelity enough that you could do optimization over it. So what they're going to do in this case is they are sort of solving the offline case by constructing, here not necessarily from data, more maybe from a physics model, a simulator. So we're going to do kind of like model-based RL, model-based in the sense that we have to have a model or a simulator. But then what they're going to do is an actor-critic method. So they are going to do actor-critic in this case, where they have a control policy, and they're also going to learn, so they have the actor here, and they're also going to be learning a critic. So I thought this was pretty interesting for why they took this particular architecture. I'm just going to read you a little bit about that part. Let me go down there. So a couple things. So I thought one of the things is they use an actor-critic method that is related to something else we saw, but not exactly the same. It's called MPO, and I'll write that out in a second. But one of the things that I thought was interesting is they said, in our simulating period, we can do sort of whatever we want, and we can have a really complicated critic. When we are deploying this, it has to be real time. So some other people, I think it was brought this up when we were chatting about it. This is like, self-driving cars, and that like you have to have really fast controllers. You can't do Monte Carlo tree search and wait for us to decide, like the plasma is going to do something. And so either you're controlling it or it is doing something else if you're not making an active control. And so they needed an actor, aka a policy that is really computationally fast. And so what they said is that inside of their actor-critic architecture, one of the reasons they wanted to do that during the training is they could require their actor to be pretty low dimensional. And so have a pretty small network to specify the actor or the control policy, which is what they're going to eventually deploy. But they could have a really complicated critic. And so they can leverage the fact that in the offline setting, they can, really in a complicated way, many parameters specify their value function because this is all offline. And so this is sort of a nice, interesting asymmetry between computational efficiency and what are the affordances you have offline compared to online. So they have a very complicated critic and they have a very simple actor. And so then they train the actor to try to find a good point in that policy space using their really complicated critic. And so they said the representation of the control policy of the actor is restricted as it must run on TCV with real-time guarantees, but the critic is unrestricted. So I thought that was pretty interesting that they had this. Now, another thing, and this came up in some conversations, is as you might imagine, if we go from offline to online, there is always the problem that it might not translate. And again, we're dealing with plasma, so we want to have some sort of safety guarantees. So here, the ideas we've talked about before about sort of having more trusted regions or having pessimism come up. And the way that they handle this is by putting it inside of the reward function. So they essentially define areas which they think could cause bad outcomes, and then they put that inside their reward function to lead to a policy that veers away from that area. And I think, again, that's a pretty common idea that if you have safety, this comes up in robotics and other ones too. Claire Tomlin up at Berkeley does this too, and a number of others. You put that inside of the reward function so the resulting policy avoid those. And so here they're doing that not necessarily because reaching that particular part would be bad, but because you're getting close to a part where it might be unsafe or where you don't trust your simulator. All right, so let's go back to here. So in this case, it's an actor-critic. Actor-critic. This is complicated. This is simple. This has to be simple for speed, and we all do this with a simulator. We put penalties in the reward to avoid inaccuracies in simulator or unsafe outcomes. And so this is very similar to sort of this pessimism over the places where we're uncertain, whether because of data sparsity or because of known problems in our simulator. We have any questions?
I guess, with like considered reward hacking or like sensitive rewards, how do you like, I guess like when you like hand trim a reward, how do you like avoid like, or how do you like double check? I assume like they really don't want to be making mistakes here.
So great question. So my guess in this case is it ends up making you just pretty conservative. Like I think of just how far away. Now I assume in this case, maybe because some of the physics simulators that they have access to, that they could play with some of sort of saying like, how negative do you need to make some of these, or how out of bounds, or how hard of a constraint is that, so that you could be very confident that before you deploy this, you make sure that this doesn't reach there. At least in the simulator, you could see whether or not you're violating those constraints, or like if you have these penalties, if you're sufficient not to reach parts of the area that you think you might want to avoid. Whether that will translate to your real system is an important question. So yeah, it's a great issue of how you. Now I think it also introduces the really interesting question of whether you can verify. So there are other methods. This is not most of what we've talked about is not those, but where you could verify that you're not going to reach unsafe regions. And this would certainly be an area you might want to do that. All right, the third one was efficient and targeted COVID-19 border testing by RL. I should have also mentioned, so this is also a multi-step RL problem. So absolutely the controls you're doing affect the next state, and that's the whole point, and then you want to manipulate the plasma into a particular location. So it's definitely a multi-step system. This one is thinking about how do you do efficient and targeted COVID-19 border testing. And even though it's via RL, it really is a bandit problem in this case. So it's a repeated bandit problem. It's a batch bandit with delayed outcomes. So let's make this a little bit bigger. So again, remember to think back what happens in this case. People come in. Greece has some information about those individuals before they show up. We have finite numbers of tests we can run and process. We have a policy for each individual coming off that plane, whether or not they're going to be given no test or they're tested. You get the results 24 hours later, and you use that to update your policy. So I think this is a really nice example of like this batch bandit process. Who you test today does not affect who arrives tomorrow on a plane. So it's a bandit problem. But we have this delayed outcome problem that like you don't observe the outcomes of who you just tested for a while, which means that algorithms like Thompson sampling may be helpful. And then in addition, some of the other really big challenges in this case is that you have a lot of constraints. You have constraints for multiple reasons. So we have constraints over the number of tests we can run. You also can have different constraints depending on where you're arriving in Greece and where you can send things. So there are different testing sites which might have different capacities. And in some cases also you might have, I don't think they dealt with this in this paper, but sometimes you might have fairness constraints too. Like maybe it's best to test all the women, but maybe that's considered unfair. And so you may have a number of different constraints that you can think of as restricting your policy class. So it's a pretty interesting interaction problem here. And also because of the fact that it's budgeted, it means that a lot of your outcomes are coupled in a way that they might not be. So for example, if you give me a test, if we only have one test that we can do in this room and you give me the test, then you can't give it to any of you. And so there's this interaction too in terms of the data that we get to observe. for the right. So I think this is a really interesting case, and it was really interesting that it ended up having a significant benefit. One of the things too that's interesting about this is sort of how we define the reward. One thing that we were talking about in our smaller groups is that really you would like to understand how this is impacting downstream COVID outcomes. And you can measure those, but you can measure those really late. Like you can use those as a way to evaluate how effective the overall program was, but not necessarily a reward you can use to optimize. And that's often a really common challenge. The rewards you get immediately that you could use to change your policy may be different than the downstream outcome you care about. And on Friday, I was at an experimentation workshop at the business school here, and I was giving a talk, and I was really excited and interested to see how many other people were also thinking of this challenge of short-term outcomes versus long-term rewards that you really care about. And I think this comes up a lot in advertising and other areas too. Companies like Netflix and Spotify and others were talking about this common challenge where you have to make policy decisions update your policy way before you can maybe observe those outcomes. And so if you have to wait a really long time, it limits how quickly you can experiment. And so in this case, too, you might really care about these downstream ones, but one of the points of this paper was to argue looking at that lagged information was allowing people to make sort of not as good decisions. And so you need these sort of shorter term outcomes. So do you have any questions about this one? So I encourage you to, if you haven't read any of those papers, they're really beautiful papers if you want to read any of them or all. And then just finally, if you remember all the way back, we talked about ChatGPT at the very beginning of the class. And I think you should feel excited now that you really understand this whole pipeline of what's possible. The first is sort of, training a supervised policy, which we could think of as behavior cloning. The second is doing direct preference solicitation. We did it with 2 pairs, and then doing PPO. And we also, of course, did DPO as well. So I think now, even though we didn't do it with large language models, you really have a sense of sort of the whole process you could use if you were to train large language models and do this sort of fine tuning. All right, so now we're just going to kind of wrap up with some of the main ideas and then looking forward. So if we think about sort of the main characteristics of reinforcement learning, this idea of learning directly from data to make good decisions, we've been thinking a lot about optimization, delayed consequences, exploration, and generalization. And I think a key thing just to remember, if you didn't remember anything else from this class, is that one of the big differences of reinforcement learning is that in general, the actions impact the data distribution. Certainly of the rewards we observe, but often also of the states we get to reach. And that's just very, very different than like supervised learning or unsupervised learning, where the data we get doesn't, you always see the label, or you just have a static distribution of data. So this is both a huge opportunity and a huge challenge because we have to think a lot more about distribution shift. So in terms of the standard settings we've seen, we've talked about bandits where the next state is independent of the prior state in action, as well as general decision processes, where the next state might depend on all the previous actions and states, or it might be Markov and it only depends on the immediate state and the immediate previous action. We've also talked a lot about the online-offline sort of settings, where either you have historical data only and you're trying to learn better policies from that, or where you can actually actively gather your own data. And I will highlight there that I think many real-world settings are sort of often between these two. So in many cases, you might have a large pool of offline data, and then you might be able to get a small amount of new online data. This comes up in robotics, it comes up in some of our work. We often call this sort of experimental design, so that you might have offline data, and then you can design an experiment to gather a small amount of data to try to learn a good decision policy. So I think in general, we can think of this as an entire spectrum between these two extremes. Now, what are some of the core ideas we've seen? Well, of course, we've seen a lot of different ideas, but I think it's nice to sort of pop up a level and think about sort of the common themes. And Chelsea Finn, who teaches DeepRL, also had a really nice slide on this, so I found that my thoughts were aligning with a number of hers as well. So one thing is just to be really familiar with the fact that when we have function approximation, which we're almost always going to need because we want to handle hard complex problems, and we want to do off-policy learning, that honestly we often want to do whether we're online or offline. And just remember, off-policy learning just means that we want to take some data that was generated from one decision policy and use it to think about how another one might work, whether in terms of gradient steps or in terms of fully offline learning. And this is generally just really hard. So you could argue that a huge number of papers in reinforcement learning just think about this problem. It's just incredibly hard. And the reason is that whenever we have a new policy, we're going to get a new distribution over state action rewards. And that means that it may not match our current data. We have a data distribution shift. And the reason we want to do this, the reason we want to have that use the offline data, is because we want to be data efficient. And this is true even if you can be online, because as we saw for things like PPO, if you follow sort of the theory or if you follow this, you often have to really be incredibly conservative or just have bad performance for a very long time. But the problem is that when we combine these two, in general, we're going to be doing generalization or extrapolation. And whenever we do that, we need to be worried that like the values, our predictions of how good a policy will not match its actual performance. And so over and over and over again, we've seen how do we try to mitigate this and in different types of methods. So like in PPO, the way we control this, and this is an online method, is we control it with clipping. We just can't take too big of a step inside of our gradients. And that allows us to make sure that we're limiting this extrapolation problem. In the Dagger case, we mitigated this by getting more expert labels. We knew that there could be a data distribution shift when we started to follow our behavior clone policy. And so we just try to get more labels when we get into states where we make decisions different than the expert, so we can kind of cover the distribution of states we reach under the learn policy. And things like pessimistic Q-learning, which came from my lab, CQL, which came from Berkeley, and MOPO, which came from other colleagues of mine here at Stanford, all introduced pessimism into offline RL. Again, exactly to kind of limit this extrapolation problem where you're sort of overly optimistic about what will happen. So I don't think you should think of these as being the only ways to solve this problem. I think what they should sort of inspire you to is to think, wow, this is a problem that comes up really throughout all of reinforcement learning. And we have some methods for trying to handle this, but this is certainly not a solved problem. Some of the other core ideas that we saw a lot was this idea of the sort of different ways we could think about the main objects in reinforcement learning. So we had this sort of models, values, and policies. And sometimes people ask me, like, do we really need all of these? Or are these all useful ideas? I think some of the application areas we were just going through illustrate why these might all be useful ideas. So models are often easier ways to represent uncertainty. So if we only have finite data and we're training something about a value or a model or a policy, often it might be easiest for us to represent that uncertainty with a model. Somebody have an idea of why that might be? Why might it be easier to represent uncertainty for a model rather than like a Q function or a policy? You could disagree with me too, but I can give you why I think this might be easiest. We're building just like a dynamics model or a reward model. Why might that be an easier place for us to represent our uncertainty about how the world works compared to trying to represent our uncertainty over the Q function or the policy?
Is it maybe just because like when you're just like, for example, like uncertainty in the policy is uncertainty both about like the world, but also uncertainty about giving your assumption about the world of what you think the best action is. And so you're just dealing with like joint uncertainty, whereas the model of the world is kind of like, it's just more like specified problem. You only have like one source of uncertainty.
Yeah, I think that's great. That's a great intuition. That's what I was going for here. So to repeat what I said here, like when you think about policy uncertainty, there's sort of that kind of combines and wraps up this idea of uncertainty over how the world works and uncertainty over what you should do to make good decisions given that world. And same for the Q function. And there are ways to directly represent your uncertainty over the policies and the Q functions, but models, it's a prediction problem. And so we have lots of tools from supervised learning and from statistics and data science to think about modeling our uncertainty when it's just a prediction problem. Like, you know, what state will happen next or what reward will I get in this state? There's no planning or decision making yet. It's just prediction. And so it's sort of a nice place for us to reduce or leverage the beautiful history of work in all the other fields of how we can do this easily instead of then having to propagate that through. So I think often this is an easier place to represent our uncertainty. Of course, there's no free lunch. And if we have it there and we want to think about our uncertainty over Policies and value functions, we still have to propagate it, but it may be easier for us to represent that and drive ourselves towards it. They're also really useful for things like Monte Carlo tree search. Like you can use models for simulators, or for plasma. You may be able to use these ones as a place to think about risky domains or to be very data efficient. The Q function, in some ways, is kind of the central part of RL in the sense that it just summarizes the performance of your policy. And you can use it often to directly act, because you just take an argmax with respect to the Q function. So it's a good way to summarize like how good things are. And policies are just ultimately what we want to have. Like we want to have good decision making. We often want to know exactly how good that is, and that's maybe where the Q function is one particularly nice thing, but ultimately we want to try to make good decisions in the world. I think another thing that's come up repeatedly is sort of this question of computation versus data efficiency. And I think one thing that it's really useful to remember is that in some cases they are the same. So in this class, I've often talked as if they're sort of totally different, but in many situations, if you have a simulator, data is the same as computation. You're either using your computation to maybe do more planning or try to get to a better policy before you simulate the next step, or you're just simulating more steps. And so I think when you look at papers, if they have a simulated domain and they're trying to do something really fancy in the back, it's useful to remind yourself that if it was a real problem you want to solve, you could either take that same computation and just have maybe 10x more samples, or you can do 10x more computation between each sample. Now, in some other cases, we really do have limited data. We just fortunately do not have 7 billion people with COVID. Like there's just a finite number of people and there's a finite number of students. And so sometimes you really want to be data efficient. When you do that, it's often trading off for computational cost. So we're going to try to squeeze everything we can out of the data. And when we do that, we often are going to rely on methods that are much more computationally intensive. And also, as you've seen, in some cases, you have real constraints on this, like in plasma, like in self-driving cars, like in robotics. There are sometimes cases where you have to have fast computation because otherwise there is a default, there's kind of a hidden action, which is you have to make a decision at every time point. If you're not doing something optimal, something else is happening. There's some default action that's always occurring. Now, what are some of the open challenges? I think there's a lot of open challenges. I think RL is a fascinating area, but RL has not yet had the applicational impact that we've seen in some other areas of AI and engineering. And I think this is for a number of reasons, but one of them is that you really want methods that are off the shelf and robust and reliable. And many RL algorithms have hyperparameters. You have to pick the learning rate. You have to pick, there's some of these are the same as normal machine learning, and others of them are different. And one of the challenges here is if you're online, even though in our world, like when we're doing a homework, you might be able to try it with different hyperparameters. In a real world setting, like for healthcare or for customers, you would just have that one trajectory. And so in that case, or one deployment, you can't sort of optimize those parameters. And so I think that there's this real need for sort of automatic hyperparameter tuning, model selection. By that I mean, how do you figure out what architecture you use? How do you even write down the problem? And generally robust methods, model selection are like, the size of your neural network, et cetera. And just general sort of robust guarantees that we're not going to suddenly have one run where your performance is really bad. The other is that we often need things that are going to be able to span this data versus computation efficiency. And we don't normally have very good ways to allow a practitioner to say like, okay, well, this is how much I care about this or that. It'd be really nice if we could have sort of like Pareto frontiers. And you could say, well, if this is computation and this is data, you might say, okay, I want to have things that are always somehow optimally trading off between those two. And depending on my application area, I can pick where I want to be on this curve. And I also think this hybrid offline-online case is a really important one, where many organizations might be willing to do a little bit of additional data collection, but not fully online learning. I think there's also some just really big questions for reinforcement learning. We focused a lot on the Markov decision process formulation. That's where it comes out of the 1950s and Bellman. That's how I learned about it. Many people learned it. And it has some really nice intellectual properties, but it is not clear that this is the right way to solve data-driven decision-making. This is one framework. So I had a professor when I was a grad student who said that the whole world is, a multi-agent, partially observable Markov decision process where you're doing learning. But it doesn't mean you want to solve it like that. And so while in many times we might be able to model things in these kind of stochastic Markov decision process ways, that may or may not be the most efficient way to represent the problem. It's just like how you could always represent a bandit as a really complicated RL problem. But if your next states are independent of your previous one, why would you do that? So I think there's some real questions over, are there better formulations? I think a second thing is that historically in reinforcement learning, and even throughout most of this class, we focused on, I'm going to learn from this one task from scratch. But of course, that's not what humans do. We constantly are building on our prior experience. We are sort of imperfect agents for learning across many, many, many tasks. And what we've seen from generative AI, large language models, et cetera, is that doing many, many tasks might be really powerful. And that's been relatively understudied in the RL setting, and it might be much more effective. We've seen even in AlphaZero and AlphaTensor and others that these shared representations can have huge benefits. And so those might be really productive ways to think about accelerating the speed of decision-making and learning good data-driven policies. I think a third thing is thinking about alternative forms of feedback. Assuming you get single scalar rewards is pretty limiting. Particularly now that we have large language models, you could imagine having really rich feedback or really sparse feedback, like thumbs up, thumbs down, or preference pairs, or really detailed examples about how something is wrong or what your preferences are. And now that we can start to have language as rewards, I think that's a much richer opportunity. And people are starting to explore this already. Another is sort of just what settings we're in. Most of this class, we thought about stochastic settings. Take an action from a state, you get to some next state generated sort of stochastically from some sort of indifferent process. But that's not very common in real world settings. In many real world settings, there are other stakeholders or multi-agents that might be adversarial or might be cooperative. You might have a teacher that's helping the agent learn something, or you might have an adversary that's competing with that agent. And so those settings are also really important to consider. And I think another question too is, throughout this class, we've been thinking about sort of integrating and doing learning and planning and decision-making all at once, everything. And that's wonderful and elegant, but there are many approximations to this. So in some other fields, they often do system identification. I mean, you might learn how the Markov decision process works. You learn your dynamics model, you learn your word model. You stop, you plan. And so while this offers some flexibility, it also introduces a lot of complexity. And again, in some areas, there might be some really good alternatives to this. And finally, this is one that's perhaps closest to my heart, which is I think that there's just an enormous room to do better data-driven decision-making in domains that could benefit. So I think there are lots of application areas we've talked about in class, but there's so many areas where I think our society could benefit from better decision-making. And so it'd be incredible to see more of that impact, whether it's from the frameworks we've covered in class or from others. And I think one of the wonderful things is that you guys are very well equipped now to go out and start answering these questions or other ones that you think are important. All right, I'll just close with two more slides. One is that if you like reinforcement learning, there is a lot of people at Stanford who think about reinforcement learning. There are lots of classes. There's at least another 5. So there's Deep RL with Chelsea. There's Decision Making Under Uncertainty with Michael. Michael and I both offer advanced courses in either decision making or RL. And Ben Ryan Roy often also offers an advanced RL or Bandit class. So there's lots of places to learn more. And finally, thanks for being part of the course. It's great to get to meet everyone. And we're really excited to see your posters on Wednesday. Thanks.